In the first two parts of this chapter, we have learned how to find out the areas and volumes using integration. However, the earlier examples involve only graphs with equations given in Cartesian form, i.e. y equals to fx. Now, we are going to take a look at how to find the area and volume in questions where graphs are given in parametric form instead. Let's do a quick recap of the formula for finding areas and volumes. For this case, on the top left, we can find out this area using the formula A equals to integrate from A to B y dx. And for this diagram on the right hand side, we can find out the area using A equals to integrate from C to D x dy. For the bottom left volume over here, we can find out using V equals to integrate from A to B pi y square dx, since it is revolved about the x-axis. And for the bottom right case over here, we have V equals to integrate from A to B pi x square dy, since it is revolved about the y-axis. However, if we are given parametric equations instead, how can we find out the areas and volumes? The answer is not too complicated after all. We should start with the exact same formulas as earlier, then do a substitution and subsequently integrate by changing all the x and y's into the new parameter. In a way, this is exactly like performing integration by substitution. For example, if we look at these two regions of interest over here, how can we find out the area and volume respectively? For this area over here, we can start with A equals to integrate A to B y dx, which is the same exact formula as earlier. Now let's perform a substitution. The A and B values are actually x values, and therefore we have to change them into corresponding t values. So when x is equals to A, we get a corresponding value of t, which let's say it is TA and TB respectively. Y can be changed into GT because we know that y is equal to GT. And finally, for dx dt, we can find out dx dt very easily as f prime t. And therefore, dx can be written as f prime t dt. And now what we have to do is just to solve this integral, and we will get the corresponding area. Likewise, the volume over here can be found using integration of a to b pi y square dx, which can be changed into integration of ta to tb pi y square becomes gt whole thing squared, and dx becomes f prime t dt. And again, once we solve this entire integral, we will get the volume of this region. In example 1, we have the curve defined parametrically as x equals to 2t squared and y equals to sine of negative t for t more than or equals to 0. And we are asked to find the exact area that is bounded by the curve, the x-axis, and the line x equals to pi squared over 8, which means we are looking at this region over here. To find this area, we can use the formula A equals to integrate y dx from 0 to pi square over 8. So let's start by writing A equals to integrate 0 to pi square over 8 of y dx. Now we have to change everything in terms of t, which means that pi square over 8, which is an x value, it is going to become pi over 4, and 0 is going to remain as 0. And this y over here, it will become sine of negative t, and this dx, it is going to become 4t times dt. And therefore, this integral can be transformed into integration from 0 to pi over 4 sine of negative t times 4t dt. And we can invoke a property of the sign to bring the negatives out. And this gives us integrate 0 to pi over 4 negative 4t sine t dt. For this integral, we will have to solve using integration by parts, and eventually, if we work everything out, we will end up with the term pi over square root 2 minus 4 over square root 2. However, there is one thing to note, that is this value over here is a negative value. This is because the region is below the x-axis, which we have learned that since it is below the x-axis, we will get a negative area if we perform any integration. Therefore, what we can do now is to simply just put a pair of modulus across all our working over here. And therefore, this will give us 4 minus pi over square root 2 square units. In this next example, we have another curve defined parametrically. The region S is bounded by the y-axis, the curve, and the straight line y equals to half x, which tells us that it is this region over here. And we are going to now revolve this region about the y-axis to form a solid of revolution. And how can we find out the volume of this region over here? Let's find out. Firstly, we note that the region S can be divided into two parts. The top part being bounded by the curve and the bottom part being bounded by the straight line. So the volume of region S when it is revolved about the y-axis is simply the volume of the curve when it is revolved about the y-axis plus the volume when the straight line is revolved about the y-axis, which is basically just a cone. Therefore, we can find out the volume of this very easily using v equals to integrate 0.5 to 1 pi x squared dy, which gives us the top part of the volume plus 1/3 pi r squared h, which is the volume of a cone for this bottom part over here. Now let's perform the substitutions. When y is equal to 0.5, t will be equals to 1. When y is equals to 1, t will be equals to 0. Pi remains as pi and x becomes t cubed. So t cubed square multiplied by dy, and dy we have to change it into negative 2t over 1 plus t squared whole thing squared dt plus 1/3 times pi times 1 square times 0.5. Now note that in the question there is a very important keyword, that is we are asked to find out the area correct to 2 decimal places. This tells us that we do not have to perform the integration, but rather we can make use of our GC to evaluate the final value of this integral. So therefore, let's use our GC and solve this integral, which will give us 0.773, which can be rounded off to 0.77 units cubed, which is the volume of region S when it is revolved about the y-axis.